Welcome. How non-destructive testing works, the essentials. Fired heater tubes run for years above 800 degrees. Creep voids, carburization, cracks, thinning, all invisible from the outside. We cannot cut every tube. NDT finds and sizes the damage, in service. No cutting. Just physics. 5 methods cover most inspections. Ultrasound listens for echoes. Radiography sees through metal. Eddy current senses electromagnetic disturbances. Penetrant bleeds from surface cracks. Magnetic particles trap leaking flux. The physics decides what each method can find. Chapter 1. Ultrasonic Testing. A piezoelectric crystal turns a voltage pulse into vibration, our sound pulse. It travels through steel at a precise velocity, about 5,900 meters per second. Velocity is known, so time becomes distance. And whenever the wave meets a change, a crack, the back wall, part of it reflects. All of UT builds on those two facts. Watch one measurement. The pulse travels down the beam. There, it hits the crack and reflects back, the flaw echo. The rest continues to the back wall and returns later. Initial pulse, flaw echo, back wall echo, always in order. Position gives depth, height relates to size. Two probes do most of the work. Straight beam, sound goes straight down, for thickness, laminations, corrosion. Angle beam, a wedge steers shear waves at an angle, and the beam zigzags through the wall, covering the full volume to catch cracks. How does an echo become a number? Measure the time, for microseconds. Depth equals velocity times time divided by 2, because the sound went there and back. That is 11.8 millimeters. And before every job, verify on a calibration block. One reading is useful, 1,000 are powerful. Mark a grid, take a reading in every cell, and color by remaining wall. Watch the map build. Green is healthy, and there, a corrosion patch, minimum 6.6 millimeters, ready for fitness for service assessment. Phased array, many elements fired with precise delays, and the beam steers electronically, no moving parts. And guided waves, a collar sends waves along the entire pipe, screening tens of meters from one position. Even far-side defects reflect back. Chapter 2. Radiographic Testing. X-rays and gamma rays are absorbed exponentially, I equals I naught, e to the minus mu x, thicker metal, fewer photons. Where a void or crack sits, less metal blocks the path, so more radiation reaches the detector there. Source above, detector below, IQI wires on the part. Exposure begins. Watch the density build. The void exposes darker, the crack shows as a fine line, the IQI proves the image is sensitive. A permanent picture of the inside. Reading film is a skill of shapes. Porosity, round spots. Slag, an elongated band. A crack, thin and jagged. Lack of fusion, a straight line at the weld edge. Dark means less material, and the shape tells you the flaw. Dose follows the inverse square law, double the distance, quarter the dose. Time, distance, shielding, and respect the controlled area. Radiography demands discipline. Chapter 3. Eddy current testing. An alternating current in the coil creates a changing magnetic field, which induces eddy currents in the metal. They concentrate near the surface, the skin effect. A crack diverts the flow, and the coil's impedance changes. That impedance is what we measure. The coil scans the tube, the impedance dot sits at balance while the metal is sound. Now watch the crack. The current is diverted, the impedance changes, and the dot traces a loop, the defect signature, carrying depth and character information. Then it settles back to balance. An array packs many coils in one probe, fired in rapid sequence. The C-skin builds in real time, every defect mapped in position and amplitude. One pass, wide coverage, at production speed. Chapter 4. Dye penetrant testing. Step 1, clean. Anything left on the surface blocks the dye. Step 2, flood with penetrant. Capillary action pulls the dye into the crack. Dwell, 10 to 30 minutes. Step 3, remove the excess. The crack keeps its dye. Step 4, the developer, a white blotter, pulls the dye back out. Step 5, inspect. A red stain bleeds out, many times wider than the crack itself. The physics amplifies the flaw. No surface crack can hide. Chapter 5. Magnetic particle testing. One rule matters, direction. Flux crossing a crack is forced out of the surface, a leakage field that traps particles. The same crack parallel to the flux is missed. So we always magnetize in two directions, 90 degrees apart. Clean the part, apply the yoke, and the component becomes a magnetic circuit. Watch the flux flow, and where the crack cuts across, it leaks out. Now dust on magnetic particles. The particles migrate and pile up at the leakage field, the rest wash away. And under UV light, the crack glows bright green. Unmistakable, as long as the steel is ferromagnetic. Side by side, UT is deep and quantitative. RT gives a permanent image. ET is fast and contactless. PT is simple and cheap. MT is extremely sensitive. No method wins everywhere, so real inspections combine them. In the fired heater, every damage mechanism has a physics that finds it. Creep, ultrasonics and replication. Carburization, eddy current. Cracking, PT, MT, arrays. Thinning, a UT grid. Bowing, laser profiling. Then the data feeds API 530 and 579. Inspect, detect, predict. Five methods, one goal, find the flaw before it finds you. Thank you.